In Chapter 6, we will be discussing all about sketching. So putting together the information that we have about the derivatives and producing a fairly accurate and detailed graph of a function. Let's start by talking about just the overall shape of the function. We've already we've used this vocabulary of functions increasing and decreasing, and that's a fairly intuitive notion. If a function is increasing, it can increase, for example, in this way. We understand this as a trend as the function goes upwards, but the function can also increase in this way. The one way to describe an increase really is just to think about tangent lines. And in both of those cases, the tangent lines have positive slope. Positive slope of a tangent line means the derivative is positive. So if someone tells you that the derivative of a function at a certain interval is positive, you know it's increasing. But that's not enough information to distinguish between the two cases of the very different type of increase that the function can take. So let's think about the next step. What can I say about these two functions to really differentiate between these two cases? Let's look not just at one tangent line, but at maybe 2 or 3 tangent lines to the same graph. So in this case, let's draw another tangent line later on. And now let's look at these cases as drawn now. So we can see that here tangent lines start off shallow and get steeper and steeper, whereas here it's the opposite. They start off being steep, and then as the function plateaus, the tangent lines also get shallower and shallower. And that is going to be our essential difference between those two cases. How does the derivative grow itself? Does the derivative become higher, a bigger number, or does the derivative get smaller? So thinking about the rate of growth of slope, really have to pause for a second and decide what is it that we're really discussing here. The slope itself, the slope of a tangent line, is the first derivative. The rate of growth of something is a derivative of that. So in order for us to distinguish between those two cases, we have to discuss the second derivative of the function. So this will break up into 2 cases depending on what the second derivative behaves like. So in this first case here, the derivative itself grows higher and higher, which means its rate of change is positive. So the rate of change is positive, and it's the rate of change of a derivative. A derivative of a derivative is just a second derivative. So instead of having this notation, we can simply say f prime prime of x. Okay? And in the second case, the rate of change of the slope is negative because it gets smaller and smaller. So that means that our second derivative in this case is negative. In fact, I'm not going to include the 0 here. That's the case we're going to discuss separately. Okay, so when the second derivative of the function is positive, this corresponds to this shape, and we call that upwards looking shape concave up. The second case, when the derivative is negative, corresponds to this case where the function is sort of looking down. So we're calling this concave down. In case of a function decrease, the situation is going to be very analogous, except for reversed. So in order to try to follow this logic, maybe pause the video for a second and see if you can create the exact same column, but for a negative first derivative and the 2 cases for the second derivative. Now, of course, you can see here now that it's very, very similar. So for this first function, the derivative is always negative. But as time goes on, it becomes less and less negative, meaning that it's actually increasing. So the second derivative is positive, whereas the second case, the second derivative gets steeper and steeper, which means it's becoming more and more negative, and therefore the second derivative itself is negative. So those are the 2 main shapes that will be describable by a second derivative. Concave up, meaning that your function sort of looks like an upward cup, and concave down means that it's facing downwards. In terms of special points on the function, we will talk about local extrema and global extrema. Extrema means maximum or minimum, and these are rigorous definitions of what it means to be minimum and what it means to be maximum. Essentially, what this is saying is that a local maximum is the point that is the highest point around. So if you look at points near it, point X is on some sort of a peak, whereas local minimum means that for all the points near it, that's the lowest point around. Global behavior means it's the highest point in the entire domain or on some specified region. Now, thinking about what we described on the previous slide as the general behavior of the function and thinking about these special points, how does the function get to a local maximum or a local minimum? So if we're thinking about one of these peak points around, what happens to the function before and after? So let's think, for example, about local maximum. In order for the function to have a local maximum, it means that the function has to increase up to that point and then decrease afterwards. Okay? Now, thinking back to the previous slide, there's a couple of ways that that can happen. So we will actually have a number of different possible cases for increase followed by a decrease. Let's try to describe just a few of them. Now, the function could have increased in, for example, this way to the point of local maximum, and then decreased in this way afterwards, which formed the local maximum in the middle. The function could have also increased, for example, in this way to the point of local maximum, and then decreased like this. Take a minute here, try to come up with other possible cases for the function to increase and decrease that will look qualitatively different from these two graphs. Now, the one thing that they will have in common is increase is described by first derivative being positive. So on the left-hand side here, this means that the derivative of the function is positive as the slopes of the tangent lines are positive. And the decrease is described by the derivative of the function being negative. Function's derivative going from positive to negative through this point in the middle is what creates a local max. Okay, so these are again not the only two cases where a function can acquire a local maximum. Try to also come up with cases for a local minimum. That is, of course, when the decrease will be followed by an increase, but you have choices for what the function looks like concavity-wise on the decrease and on the increase. Now, thinking about these two cases, though, then what happened at the top is that the tangent line here is actually horizontal, which means that in this case, the derivative at the local max was 0. Whereas in the second situation, the derivative is the slope of the tangent line at this point, but this is a corner. This is exactly one of the cases when the function is not differentiable. I cannot draw a unique tangent line. I wouldn't know which way it goes. So this case corresponds to the function's derivative at the peak does not exist. And this motivates us to come up with a useful definition of a critical point that will describe both of these cases. So a point is called a critical point if, first of all, it's an actual point on the graph, so the function value has to exist at that point. And second is description of these two cases. Either the derivative is 0, which means that the tangent line is horizontal, or the derivative does not exist, which means that I cannot construct a tangent line there, but I might have hit a local peak or local value. Now, first derivative test tells us how to turn the information that we gathered on the previous slide into actually classifying a point as local maximum or local minimum. So the first derivative test says that a critical point, which is where the derivative is either 0 or does not exist, is an extremum, meaning it's maximum or minimum, if the derivative actually changes sign at p. So notice that it's not that the point is critical that determines whether it's a maximum or minimum. It's the fact that at that point, derivative goes from positive, for example, to negative, or the other way around. So let's take a look at those two cases. The first one, the derivative goes from negative, which means the function is decreasing, to positive, which means the function is increasing. So for example, one case like this would be like that. Could be other cases. I again encourage you to be able to draw them out. So in this case, because it went from negative to positive, we're acquired a local minimum. In the second case, it's the other way around. The function goes from positive, which means the derivative goes from positive, which means the function is increasing, to negative, which means the function is decreasing. And then you have the exact opposite picture here, where it goes from positive to negative, and then the point turns out to be a local maximum. Okay, so be very careful. Just because a point is a critical point, it doesn't mean that it's going to be a local maximum or a local minimum. It could be neither. For example, a derivative might not exist and an asymptote, it does not make it a local maximum or minimum. Now, for a more practical example, let's take a look at a particular function and find all local extrema. So once again, that means minimum and that means maximum. The first step is to find critical points and then discuss the behavior around them. So the very first thing we're going to do is find critical points and recall that there's two cases, when the derivative is positive and when the derivative does not exist. So first of all, I have to find my derivative. So it's going to be, in this case, 3x squared minus 6x. And now I have to solve for when the derivative is 0. So 3x squared minus 6x is 0. I can factor out 3x, x minus 2. And so I'm going to get two roots. X is 0 here, and x is 2 here. So these are my two critical points from this case. And then my second case is when the derivative does not exist. Now let's take a look at my derivative here. It's this right here. It's a quadratic function, a parabola on a graph. There are no x values that I cannot plug in here, which means that the derivative will exist everywhere. So the second case produces no solutions. Okay, so my two critical points are x equals 0 and x equals 2. And the next thing, according to the first derivative test, that I have to do is figure out, does the derivative change sign around 0 and does it change sign around 2? So what happens before 0 and after 0? What happens before 2 and after 2? The easiest way to do this is to create a little line diagram, okay? So I'm going to draw a number line and put all of my critical points that I've just found on the number line. So my points are 0 and 2. What I care about is the derivative's behavior around these points, and what does that actually mean for the function. So on the side here, I'm going to keep track of the sign of the derivative because I only care about whether it's positive or negative. I don't care about the actual value. And I'm going to keep track of what that means in terms of the behavior of the function. Okay, so there's a couple of ways of actually producing the rest of this graph. I find that the easiest one is to think of the points in different regions. So these critical points 0 and 2 have divided the entire number line into 3 regions. This one, the middle one, and the right one, okay? So I'm going to pick a point in each region and figure out whether my derivative at that point is positive or negative. What is true of one point in this region will be true of all points in this region that were separated by the critical point. Okay, so pick a negative number here before 0, minus 10, and we're going to plug it into our derivative. So is this going to be positive or negative at minus 10? Again, I don't actually care about the value itself. I only care about whether it's positive or negative. So if you plug in minus 10 here, I'll notice that that gets squared. So that's 100. 300 minus 60, that's still a positive number, which tells me that the derivative here is positive. Now, you're going to do the exact same thing for the other 2 regions. So now we have to pick a point between 0 and 2, for example, 1, and plug it into our derivative. Is it going to be a positive number or a negative number? I plug in 1, I get 3 minus 6, that's negative, so this is going to be negative. And then finally, for the last region, I have to plug in number in here, so let's say 3. you plug it in, you'll see that it's going to be positive. So what does that mean for the function itself? If the derivative is positive, that means the slope of the tangent line is positive, which means that the function itself is increasing. When the derivative is negative, it's decreasing, and when the derivative is positive, again, it's increasing. And now you can essentially just trace what that means in terms of the shape of the function, right? So if it was first increasing and then decreasing, obviously at that point, we've encountered a local max. If it was decreasing and then increasing, here we've encountered a local min. Okay, so it is the change in sign of the derivative that produces either a local minimum or a local maximum. So here our answer is, for all the local extrema of this function, we have local maximum at x equals 0, and we have a local minimum at x equals 2. Second derivative test will also allow us to classify whether a given critical point is a local minimum or a local maximum. So it's an alternative to the first derivative test. The assumptions are slightly different. We're first of all supposing that we can in fact take the second derivative, which means the first derivative is differentiable. And we're also supposing we have a point at which the derivative is 0, which means we have a point at which the tangent line is horizontal. So then what are the conclusions? We have two cases. Either the second derivative is positive, which means the function is concave up, so it has an upwards cup shape. Now on this shape, the point where the tangent line is horizontal has to be this point at the bottom, which means that this case results in a local minimum. And analogously, the second case is the reverse version of this. If the second derivative is negative, it means that the function is concave down. And the point where my tangent line is horizontal turns out to be a local max. So this is another way to check for whether a critical point is a local minimum or a local maximum. You can use the first derivative test and check the behavior around the function's critical points, or you can apply the second derivative case in the case where the critical point was found using the fact that the derivative was 0. The other thing that the second derivative is very useful for is in production of better detailed graphs. So critical points are extremas if the first derivative changes sign around them, a point at which concavity or the second derivative changes sign is called an inflection point. So once again, let's go through a particular example here of the same function as from the last slide. So I have x cubed minus 3x plus 1. I'm going to look for concavity changes. And this process is going to be mimicking the process from the last slide almost exactly, except for I will be doing this entire analysis with second derivative as opposed to the first one. Okay, so first of all, I'm going to find the second derivative. To find second derivative, I have to go through the first. So the first derivative being 3x squared minus 6x. Then the second derivative is 6x minus 6. So my potential inflection points are exactly where the second derivative is either 0 or does not exist, more or less. So let's take a look at this. Where is this 0? I have to solve that. So 6x minus 6 is 0, which will produce x equals 1 as my potential inflection point. And I'm also going to look for cases when the second derivative does not exist. They might or might not be actual points, but they will tell me about concavity changes, and I have to analyze those. So here, we're still dealing with the polynomial. 6x minus 6 exists everywhere, so this case will produce no solutions. Okay, and then because I'm looking for concavity changes around the potential inflection points, I'm going to do the exact same thing as last time and draw myself a number line. I'm going to put the points that I've just found, and these are what I call potential inflection points, or PIPs. They're potential for now because I don't yet know if the concavity actually changes at those points. So I'm going to put all the points that I found here, which in this case is just one, on my graph. And then I'm going to do the exact same type of analysis, but on the second derivative, not the first, okay? So this one potential inflection point split my entire number line into two pieces. So I'm going to find a number from this side to plug in and a number from this side to plug in. The best number to plug in, if it's possible, is 0. 0 lives out here. So I plug in 0 into here. I get -6. Again, I'm not after the value. I'm actually just after the sign. So this says that the second derivative there is negative. If I find a number here, let's say 2, I plug it into here. I get a +6. So the second derivative on this side is positive. Second derivative describes concavity. It's negative here, which means that on this side, the function is concave down. And it's positive here, which means on this side, the function is concave up. So this is an actual point on the graph. I can plug it in and figure out the value. And concavity did change from down to up, which means that this, in fact, is a full-fledged inflection point. Now, let's try to put all of this information together and sketch a graph of this function with everything that we've just found out. What I found from previous information is that these are the local max and min, and 1 is my inflection point. So I'm going to try to put all of this on the graph. Now, before I start putting on the scale, I'm going to have to think about what are the points that I'm interested in. So I know 0, 1, and 2 in terms of x values are the points of interest. So I'm also going to compute f of 0, f of 1, and f of 2. So I know exactly where to sketch those in terms of the y coordinates. Plugging them in, I can see that f of 0 is 1, f of 1 is -2, and f of 2 is -3. Once you have some points on the graph to work with, I strongly recommend labeling them with what you found them to be so you don't lose track of that information. So what we found out was that 0 was a local max, 1 was an inflection point, and 2 was a local min. Okay, and now all I have to do is actually trace these shapes and put them all together organically onto this graph. So I noticed that up until this point, the function was supposed to be increasing, and it's supposed to be increasing in the concave down manner. So here I'm going to have something that looks like this, that I have to form a local maximum, which means that after 0, the function is decreasing, but it continues to decrease in the concave down manner until point 1. So it decreases from concave downwardly until 1, at which point I then have to start decreasing, but in the concave up manner until point 2. So my concavity here changes, and then after point 2, the function is increasing, and it's increasing in the concave up manner. So that way. Okay, my graph is not the smoothest. It's supposed to be a fairly smooth curve, but you get the idea. So you notice how at the concavity change, it went from concave up to concave down. Sorry, the other way around. From concave down to concave up. And the rest of the information matched what we found in the two derivative tests. One good thing to always keep in mind is that if you somehow cannot resolve all the information you found on the graph, somehow your graph pieces don't quite work together, it means that you've probably made a small mistake somewhere in your analysis, and potentially one of your signs is a little bit off. So if you cannot make it work on the graph, do go back through and rework your algebra, because that's likely where the mistakes lie. Okay, so the graph is yet another way to make sure that your analysis was actually correct.
Much like with almost all topics in math and calculus in particular,
The more practice, the better. So let's do a couple more examples of finding local extrema and inflection points of different functions. So here I have a polynomial. Again, the first step is to actually take the derivative. So I have my function and its derivative. So here for the derivative, I will have 4x cubed minus 4x. Okay, remember the powers come down and get multiplied by the coefficients in front of them. So in order for me to determine critical points, I'm going to consider the two cases when the derivative is either 0 or does not exist. Okay, and what are the solutions that are produced by both? So when the derivative is 0, I'm going to set my derivative to be equal to 0. And remember, don't divide, factor. So factoring out here, I can take out 4x. So if I take out 4x, I'm going to end up with x squared minus 1. This is equal to 0. And now, once I have a product, either the first part of that is 0 or the second part of that is 0. So the first will give me x is equal to 0, and the second will give me x is either plus or minus 1. So those are my solutions, 0, x is equal to 0, plus or minus 1, and those are going to be my 3 critical points produced by the first case. The second case of the derivative not existing, well, this is a polynomial, so there are no problematic points, which means that here I will obtain no additional solutions. Now that I have all of my critical points, I'm going to draw myself the line graph and analyze the behavior of the function so that I can classify these critical points as local extrema or maybe as none. So what do I have? I have -1, I have 0, and I have +1. And I am interested in the behavior of the derivative and therefore my function around these points. So as before, notice that if I have points splitting up my number line, I actually am creating these intervals. So for the behavior of the derivative, all I have to do is pick a point in this interval, any point you wish. So for the intervals that extend into infinity, it's actually easy to think of like a large negative number here. We're going to plug that into our derivative, and all we're interested in is whether or not it's going to produce a positive or a negative number. I don't actually care about the number itself. All I care about is its sign. So if I plug in like -1,000,000 into the derivative, it's actually easier to analyze in the factored out form. -1,000,000 squared will be a positive number. A giant positive number -1 will still produce a positive number. So this bracket will still be positive, but -1,000,000 here will make the entire expression negative. So this will be negative. Now, I've done this enough times that analyzing qualitatively like this is very convenient and comfortable for me. But if you prefer to pick a number here and plug it in using your calculator instead, by all means do just that. Okay, so if you pick a number here, for example, -1/2, plug it into this entire expression, we're going to see that the entire expression will come out being positive. For the next region, I can pick, for example, 1/2 and plug it in. I will see that the derivative ends up being negative. And finally, I will get the positive number on the other side. Now I get to interpret these signs for the derivative as the behavior for the function itself. If the derivative is negative, it means that the function is decreasing. When the derivative is positive, it means it's increasing, negative, decreasing, positive, increasing. And now, following the actual behavior of the function, I can see that it was decreasing and then increasing, which means that at this point, -1, which is a critical point and is a point on the graph, I will have myself a local minimum. Then, going from increase to decrease, I have created a little hill. So the top of the hill, being the critical point at 0, will be a local maximum. And then finally here, the decreasing and then increasing creates a dip, and the bottom of it will be a local minimum. Okay, now be careful when classifying as local minimum and local maximum that these are actual points on the graph. If this was an asymptote, this would not have been able to be a local minimum despite the fact that we're seeing the correct behavior of the function around it. Okay, so we are done with the local extrema part of the question. Next, we're asked about inflection points. Inflection points are found using the second derivative. So the first thing I have to do is find the second derivative of my function. I'm going to take the derivative and take a derivative of it. So I'm going to end up with 12x squared minus 4. And the potential inflection points are produced by the derivative, the second derivative being 0, or the second derivative not existing. So mind you, I always will have these two cases. So for the second derivative being 0, I will set it to be 0. And there are a number of different ways to actually produce the solution to that. But let's say I am going to move 4 over. So I have 12x squared is equal to 4. Divide both sides by 3 and carefully take the square root of both sides to obtain two solutions, plus and minus square root of 1/3. So these two are my potential inflection points, okay? Remember that with critical points, I actually get the critical points immediately, but with the second derivative, I don't get to decide whether or not it's yet an inflection point. I have to actually go through the graph to determine whether it's an inflection point or it's just the potential one. So far, it only has the potential to be that. For the second case of the second derivative not existing, it's still a polynomial, so this will still produce no solutions for me. So all of the points that I am interested in are going to be produced by this case, and these are the ones that will go on my number line graph. So what do I have here? I have minus root of 1/3 and plus root of 1/3. I'm not really interested in what those numbers are. All I'm interested in for now is the fact that my region is divided into 3 pieces, and I'm going to analyze the behavior of the second derivative and then interpret that into the behavior of my function itself. So here, I can pick a very large negative number. Minus a root of 1/3 is going to be a small negative number. So if I pick like something like minus 100 and plug it into my second derivative, it will tell me what the behavior of the second derivative there is like. Minus 100 squared will be a positive number. A large positive number minus 4 will still produce a positive number. Again, if you're not comfortable with this kind of qualitative behavior, by all means, pick an actual number here and physically plug it in to figure out whether this as a second derivative is positive or negative. In the middle region here is where 0 lives, and 0 is always easy to plug in. If I plug in 0 into the second derivative, I'm going to get minus 4, which is negative. And if I plug in a large positive number, I will see that my function is indeed, my second derivative there is indeed positive. So in terms of the behavior of the function itself, if the second derivative is positive, the function is concave up. When it's negative, the function is concave down. And where it's positive, the function is concave up again. An important thing, just like in the first part of this question, to see here is the fact that these are not the points that are asymptotes. These are actual physical points on my function, which means that here, when the concavity changes, and this is an actual point on the function, I have myself an actual inflection point. And same for the second case, because the concavity changed from down to up at this point, it means that root of 1/3 is also an inflection point. We will draw the graph of this function later and see how we can put all of this together in the next class. But for now, if you want to confirm that your found behaviors of the function actually match its graph, by all means, pull out Desmos, graph this function, and make sure that what you have found on your line graphs here actually corresponds to the behavior of the function that you're going to see. Now let's take a look at the next example that's not actually polynomial. So this is our first example that we're seeing where the behavior might be different. So first of all, I noticed that there is a denominator which kind of is a potential problem immediately, because before I do any kind of derivative analysis, I have to note here that x cannot be equal to 0. That will be a point of non-existence on my graph, the point that is not of the domain of my function. And in fact, I can see because it's on the bottom here, this will create some kind of asymptotic behavior there. And then I'm going to move into finding the local extrema and inflection points just like I did last time. So the first thing to do is take the derivative of my function. Now there's a number of ways we can do that. We can actually put the common denominators right away and create an actual quotient and then do the quotient rule. Or we can take the derivative as is and then put pieces of it together. So taking the derivative as is, the derivative of x is 1. The derivative of 1 over x, be mindful of the fact that this can actually be rewritten as x minus x to minus 1, right? 1 over x is x to power negative 1. So now I can take a derivative of this using the power rule. The power comes down, so minus times minus 1 is a plus. And then the power gets reduced by 1, so x to the negative 2. Now, because I'm going to be after critical points, I would like to be able to solve this for being 0 and not existing. So it's probably best to rewrite it as one whole fraction. So I have 1 plus 1 over x squared. And now if I do common denominators here, I will end up with x squared plus 1 over x squared. Excellent. So now I am able to start solving for critical points. And again, I always have two cases, when the derivative is 0 and when the derivative does not exist. And this is where analyzing fractions is going to proceed in a similar manner for any kind of rational function that you see. The derivative is 0 means that this entire expression has to be 0. But this entire expression is a fraction. When is a fraction ever 0? I'm taking something and dividing by something else. When is that ever going to produce a 0? The only way that this can produce a 0 is if the top of it was 0 in the first place. Now notice that this only works if you have one big fraction. This is not going to work on an expression that has not yet been composed into one whole piece of a fraction, okay? So can't apply it to this, but we can apply it when there is one common numerator and one common denominator. So the fraction is only 0 if the top is 0. The top in this case is x squared plus 1 is equal to 0. If I move 1 over to the other side, I see that this will produce no solutions. So I get no solutions here whatsoever. My second case, the derivative does not exist. I once again have to think about the fact that this is a fraction. So I divided something by something and I got myself does not exist. When is that the case? Well, that's the case when the bottom is 0, when I was dividing by 0, right? So the case of the derivative not existing is when the bottom is 0. And again, note that I can only say that because I have one big fraction, not two separate pieces or three separate pieces or whatnot. The bottom here is x squared being 0 happens when x is equal to 0. And so in this case, this is my only critical point. So I have myself a little graph here, and the only critical point on it will be 0. And I have to analyze the behavior of my derivative and my function. So I'm going to pick a point here on the left side of 0. 0 split this interval into this entire real number line into two intervals. So if I pick a negative number, let's say minus 10, and I plug it into my derivative, what am I going to see? Minus 10 will get squared, being positive. Minus 10 will get squared here, will be positive. Positive number over positive number will be a positive number. If I take a positive 10 and plug it in, I see that the derivative will still be positive. So my function is increasing on the left of the 0 and increasing on the right of the 0. Because there is no change in behavior, it's increasing and increasing. That means that at 0, which is actually not even in my domain, I have not an extremum. Okay, so the function is in fact increasing everywhere on its domain, okay? It's kind of like it exhibits some kind of increasing behavior throughout, except for I know that I have a non-existence at 0 itself. Now, talking about inflection points. So for the inflection points, I first of all have to find the second derivative. Now, I can apply the differentiation rules to this first derivative, or I can apply differentiation rules to this version of the first derivative. Well, this one is going to be easier to take a derivative of because I can apply the power rule directly.
So I am going to do just that. The derivative of 1 is 0, and the derivative of x to the negative 2 is minus 2x to the negative 3. I can rewrite this as a fraction, minus 2 divided by x cubed. And that is my second derivative. Now I can talk about potential inflection points. And they are when the second derivative is 0, when the second derivative does not exist. And luckily here, I can actually apply the very similar type of analysis because I once again have one big fraction. The fraction is only ever 0 if the top of it is 0. But now my top is minus 2. Minus 2 can never be 0, so this produces no solutions. On the other hand, the does not exist in terms of a fraction means that the bottom of it has to be 0. The bottom is x cubed being 0, which produces x being 0 as my only case for the potential inflection point here. Okay, so once again, I have myself a number line and 0 as the only point of interest here. I'm going to analyze the second derivative and then derive the functional behavior out of it. Okay, 0, the one point of potential inflection point that I have, divides the entire number line into two regions. I can pick a point on the left here, a negative, and plug this into my derivative. What am I going to get? I'm going to get minus 2 divided by a negative number, which overall will produce a positive result. If I pick a point on the right here, like a positive 10, and plug it into here, I'm going to get a negative 2 divided by a positive number, overall producing a negative result. So I have a second derivative being positive, which means my function is concave up, and then a second derivative being negative, which means my function is concave down. So on first glance, I do have a change in concavity, which means that 0 is in fact where the concavity changes, but unfortunately, it cannot be an inflection point because 0 is not a point on my function. So the concavity does change around 0, but not at 0, because at 0, the function does not exist. Okay, so here, this is not a point, but it does change inflection, but inflection changes around it. So this is a very interesting function because what I have so far is there was one critical point, which is not an extremum. There's one point where the concavity changes around, but it's not a point itself. So overall, in terms of finding the local extrema and inflection point, this function has neither. The inflection points has no local extrema or inflection points. Once again, next time we will actually draw the graphs of this function as well. But for now, you can plot this on Desmos to make sure that your analysis agrees with what you can see the graph looking like. Now, overall, let's go over the summary of what it is that we are seeing. The first derivative, the sign of it indicates the increase and decrease of the function. The critical points have to be found by setting the derivative to be 0 and not existing. The first derivative test determines whether we have a local extrema or not. In a very analogous way, we will analyze the second derivative, but in terms of not increase, decrease, but rather concave up and concave down, the concavity. The sign indicates whether it's up or down. The potential inflection points have to be found much the same by setting the second derivative to be 0 or not existing. And the second derivative test is the one that determines local extrema. Now, it can be a little bit confusing to see the first or second derivative, quote unquote, fail. So they don't quite fail, but sometimes they don't tell us the thing that we necessarily expect. So, for example, the first derivative, so-called, fails when the derivative doesn't change sign at a critical point, and so it's not an extremum. We actually just saw a case right now. There are many other cases, but that can happen, right? So for example, again, we just saw the case with this function right here, where the derivative was always positive, and which meant that while we did have a critical point, it was not in fact an extremum. And that is totally okay. A critical point does not have to produce a local extremum. That is sometimes too much to ask of a critical point. In terms of a second derivative test, it can fail when the second derivative is 0 at the critical point, the first derivative is 0 at the critical point, but we don't really know what to make of it, okay? So it's not positive, it's not negative, it's just 0. So it's unclear what the concavity actually is. And a really simple example of that is, for example, let's say x cubed, right? So the first derivative of it is 3x squared, which means that the critical point is going to be x equals 0. The second derivative of it is 6x, which means that the potential inflection point of it is also x equals 0. But of course, this is a familiar graph. So if we draw the graph, we will see exactly what happens here. We have concave down beforehand, we have concave up afterwards. At this point, the concavity changes, but it also happens to be the case that the derivative at that point itself is 0. So the second derivative test, which we're not really going to use all that often, cannot tell us whether it's a maximum or a minimum. It cannot tell us anything at all. It is, in fact, inconclusive. But by drawing the number line and analyzing the behavior of the first, second derivative and the function itself will inevitably cause you to come up with the concrete and the correct answer. Okay, we will mostly rely on the conclusions and the analysis using the first derivative test, but we will see a few cases when the second derivative test is much more efficient and easy to implement.